before we dive into the Chapter 13 section, we're going to do a little review of aqueous solutions in Chapter 4. So as a reminder, solutions are defined of homogeneous mixtures of two or more pure substances. So those two mixtures could be in the liquid phase, aqueous phase, solid phase, gas phase. And so this definition helps us to think of solutions as more than just dumping a salt or crystal in water and it dissolving. When we have something that is dissolved in water, where water is the solvent, and as a reminder, the solvent is the thing that has the greatest abundance, where everything else is the solute. So you can have more than one solute as long as it's less abundant than the solvent. When water is the solvent, we will have an aqueous solution. There are different ways that water will dissolve substances. So either when we have ionic compounds, you're going to break apart the ions and they will dissociate. So that means to break apart. And so water is going to surround each of the separate ions. So you can see here we have an ionic lattice structure, and the waters will come and attach to them. So they're going to, the positive side of the water with the hydrogens is going to be attracted to the anions here, the negative charge, and then the negative side of the water on the oxygen is going to attach to the cation, and when that force of all these waters attacking it is strong enough, if it's strong enough, it will actually pull those ions out in solution and solvate them or surround them. So that's where we have those ions. Now molecular compounds, they will interact with water, right? Water can touch them, but but they're not going to dissociate, so they're not going to like break apart. Polar molecules will able to dissolve in water because they will be attracted to it. So how do they actually attract to the water? Well, they're going to have, if they're polar, then water will have some kind of attraction to them, especially if they have hydrogen bonding, then that attraction is going to be strong, and they can pull off full molecules from their crystal structure. Now, when they dissolve, they can either conduct electricity or not. So remember that molecular compounds they don't carry a charge. They are neutral molecules, so sucrose or even pure water, those are molecular compounds. So when they dissolve in water, well, specifically like sucrose, there's no way for charges to be carried across, and so electrons are not going to flow through the solution, or ions, and so that would be called a non-electrolyte. Now, a strong electrolyte is one that completely breaks into ions, such as sodium chloride, and so light bulbs are going to turn on very strongly because lots and lots of electrons can flow. Now, a weak electrolyte, these are generally molecular compounds, and I'm thinking in this case of one specific type. These are called weak acids and bases. And they're molecular, so like here is acetic acid, HC2H3O2. They're drawn or written with a hydrogen out front. So notice there's hydrogens in here, 3 of them. Those ones are stuck, they're covalently bound. Now this hydrogen is covalently bonded, but it's in such a way that it's weakly held. So there's a way for that one to a little bit, sometimes partially, come off and form hydrogen ion and acetate ion. And when that happens, a little bit of electricity will flow because just a small amount of ions are in solution. A way that we will quantify our concentration or our solution amount is by concentration. We want to do that because the amount of solute we have in our solution will determine a lot of the properties of our solution, which we'll get into in the end of Chapter 13. So the amount that we dissolve is called its concentration. So when we dissolve a lot, that is a concentrated solution. When we only dissolve a small amount, that is a dilute solution. So molarity is one of the ways. So molarity equals moles of solute over liters of solution. So we would write it concentration, so molarity equals moles over liters. Now this comes as 2 units. So we only write 1, big M, so I could write something like 0.1 molar is my concentration, but what that really means is 0.1 moles in 1 liter. This should look somewhat familiar to something like grams per mole for the molar mass, or grams per milliliter for density, or inches per foot. So these are all conversion factors. Now, molarity can be used as a conversion factor that go between moles and liters. And we're going to do that quite a bit. Once we get into moles, if we have concentration and volume, we can go into moles, and now we can do stoichiometry. How we make a solution is, 1, you need to know what concentration do you want to make, and 2, how much of it do you want to make. Once you know your amount, your volume, and your concentration you want to make, you can find out how much in mass you need to weigh out of your solute. So you're going to weigh your solute's mass on a scale, which will tell you the number of moles that you have for your solution. So here we go, we're weighing it out. We're going to pour it into a volumetric flask. Now this is a very accurate glassware where we know exactly the volume because we have a little line on this neck, this really thin neck, where we can fill up the water to the bottom of the meniscus. You're going to fill it up with some solvent, so you're going to add some solvent. First, actually, you add solvent about halfway up the flask to help mix it. Once it's all dissolved, now you can slowly add the water up to the line. And you know exactly how much water you add, so you know an accurate volume, you know an accurate mass, so now you know your concentration. Dilutions happen by adding solvent to our concentrated solution. So the concentration is going to lower because we increase the volume, but the moles are going to stay the same. So what happens is I have, in this case, a volumetric pipette. It's a really precise one. So we know exactly the concentration. So I'm going to add a small amount of volume, small amount of milliliters, and I'm going to have a really concentrated solution. So remember, molarity is moles per liters, and I add a certain number of liters. So I know exactly how many moles I'm putting into my new volumetric flask. Now I'm going to add a bunch of solvent, so that's going to increase my volume of my solution. By doing so, I lower my concentration, made it more dilute, hence why it's lighter. And so I have a new volume and a new concentration, but my moles of solute that I had in there is going to be the same. So you're going to need to remember that. So the book calls this MCVC for concentrated molarity and volume equals mole dilute times volume dilute. You can also do M1V1 equals M2V2. It's up to you. Just make sure you keep things pretty clear on what you're doing. So why would you want to do this? Well, one, if you want to make a really dilute solution to begin with, so a low concentration solution for some of your experiments, and this might be necessary as you're doing really sensitive experiments. You need a low concentration. It's going to be really hard to measure out a dilute solution to begin with. Scales have a lot of limitations with measuring mass. There's a lot of user error when you measure mass, and so making a lower concentration is actually not going to be as accurate as making a high concentration where you have a high amount of mass. So you can make a stock solution, which is your concentrated solution, and then you can dilute it because measuring out volume is a lot easier and a lot more precise than measuring out mass of a low amount. Also, if you want to do serial dilutions, that means you want to make a lot of different concentrations of the same compound, then it's nice to make one stock solution, and then you can make lots of little dilutions from there. So I might take out 1 milliliter of my stock, and then 2, and then 3, and then 4, and so now I have these various concentrations.